The late 1980s represented a mature phase of Western commercial aviation, a period defined less by bold experimentation than by incremental refinement and institutional confidence. Aircraft entering service during this era were not conceived as fragile prototypes, but as stable, statistically proven systems, embedded within a regulatory environment that assumed failure had been engineered out through redundancy, certification rigor, and operational discipline. The British Aircraft Corporation 111, specifically the Series 500 operated by British Airways, embodied this philosophy. It was a short-haul jet designed in the 1960s, optimized for high cycle frequency, rapid turnarounds, and structural conservatism. By 1990, the type was considered uneventful, even dull, precisely because its engineering lineage was understood, documented, and trusted. The cockpit windscreen of the 111 was not treated as a primary structural element in the same way as a pressure bulkhead or wing spar, yet it occupied a critical boundary between the pressurized cabin and the external aerodynamic environment. Its function was deceptively simple: maintain pressure integrity, provide optical clarity, and resist bird strike and aerodynamic loading across a wide envelope of speeds and altitudes. The design relied on layered glass bonded with interlayers, mounted into a metal frame and secured to the fuselage by a series of high-strength bolts. The engineering assumption was that this assembly, once installed correctly, existed in a static state for thousands of flight hours, experiencing predictable stress cycles well within its material limits. This assumption was reinforced by certification standards that emphasized ultimate strength margins rather than procedural vulnerability. The windscreen was tested to withstand pressure differentials far exceeding those encountered in service. The bolts were specified with tolerances designed to ensure clamping force sufficient to prevent micromovement under cyclic loading. In theory, the system was overbuilt. In practice, it depended on the invisible integrity of maintenance actions carried out far from the cockpit, often during overnight checks where speed and routine dulled the perception of risk. By June 1990, the specific aircraft involved had accumulated tens of thousands of pressurization cycles. Each cycle imposed tensile and shear loads on the windscreen assembly as cabin pressure rose and fell. Minute expansions and contractions transmitted through the bolt shanks into the surrounding fuselage structure. These loads were not individually threatening, but cumulative. Engineering models accounted for this through fatigue life calculations, assuming correct component specification and installation. The calculations did not account for human substitution errors that preserved nominal fit while eroding actual load capacity. The 111's cockpit layout further contributed to an illusion of containment. The windscreen was slightly curved, mounted ahead of the pilots, and visually framed by robust metal structures. To the crew, it appeared immutable, a transparent wall separating them from a high-velocity airflow that was otherwise abstract and distant. There were no tactile indicators of stress, no audible warnings of bolt preload loss, no instrumentation monitoring clamp force degradation. The system's health was inferred entirely from the absence of failure. This inference culture extended beyond the cockpit into airline operations. Maintenance manuals specified bolt diameters, lengths, and materials, but the practical enforcement of these specifications relied on technician interpretation and parts availability. The difference between bolts measured in fractions of an inch was not visually dramatic, yet mechanically decisive. A bolt that was marginally smaller in diameter could be torqued to specification, feel secure during installation, and still provide substantially reduced resistance to shear and tensile loads under pressurization. The regulatory framework assumed that such deviations would be caught through procedural compliance. Inspection regimes focused on corrosion, cracking, and visible damage, not on dimensional verification of every fastener. The windscreen, once installed, became a closed chapter in the aircraft's maintenance narrative. Its continued presence was taken as proof of correctness. The broader context of aviation safety at the time reinforced this complacency. Catastrophic failures were increasingly rare, and when they occurred, they were often attributed to complex system interactions rather than basic hardware errors. This fostered a belief that modern aircraft no longer failed in simple ways. The idea that a cockpit windscreen could be expelled wholesale under routine cruise conditions seemed anachronistic, more appropriate to early jet experimentation than to a flagship European carrier's scheduled service. On the morning of June 10, 1990, the aircraft prepared for a routine flight from Birmingham to Malaga. Weather conditions were benign, operational tempo normal. Nothing in the pre-flight checks indicated latent structural vulnerability. The pressurization system functioned as designed, the cabin sealed, the cockpit calm. The windscreen, outwardly unchanged, bore the accumulated history of maintenance interventions invisible to those who trusted it most. This was the architecture of confidence, a layered construct of engineering margins, procedural assumptions, and cultural trust. Each layer was individually rational, yet collectively fragile. The windscreen did not fail because it was poorly designed in principle. It failed because the system surrounding it treated correctness as a static attribute rather than a continuously defended condition. In that space between theoretical robustness and practical execution, a small discrepancy was allowed to persist, accumulating significance with every uneventful flight. The aircraft climbed through the lower atmosphere, transitioning from aerodynamic loading dominated by air density to loading dominated by pressure differential. The fuselage expanded microscopically, the windscreen assembly responding as it had countless times before. No alarm sounded. No vibrations betrayed the approaching limit. The illusion held, reinforced by history, statistics, and habit. What remained unseen was that the margin between load and capacity had been quietly consumed, not by extraordinary stress, but by ordinary operation applied to an assembly that was never quite what it was assumed to be. In aviation, confidence is often mistaken for safety. The 111's windscreen was certified, installed, and flown within all expected parameters. Yet safety existed only as long as the physical reality of bolts, threads, and clamping forces aligned precisely with the abstractions of manuals and drawings. On that morning, they did not. The aircraft continued its climb, carrying with it the cumulative consequences of an error measured in millimeters, poised at the boundary where structural integrity yields not gradually, but instantaneously. As the aircraft accelerated along the runway and transitioned into climb, the aerodynamic environment shifted from ground effect turbulence to a regime dominated by steadily increasing dynamic pressure and a rapidly growing cabin-to-ambient pressure differential. The 111's pressurization system, mechanically simple by modern standards, was designed to raise cabin pressure smoothly as altitude increased, limiting the rate of change to protect both structure and occupants. This gradual rise masked the true magnitude of stress accumulating across the cockpit windscreen. What the system controlled was the rate of pressurization, not the distribution of load within individual fastening elements. At approximately 14,000 feet, the pressure differential across the windscreen reached a level that was still well below its certified ultimate strength. From a purely design-based perspective, there was no reason for concern. However, structural integrity is not governed by nominal design values alone. It is governed by the weakest load path available at the moment stress is applied. In this case, that path ran through a series of bolts whose dimensional characteristics no longer matched the assumptions embedded in the original stress calculations. Each bolt securing the windscreen functioned as part of a closed mechanical loop. Torque applied during installation generated clamping force, compressing the windscreen assembly against its frame. Under pressurization, outward force acted on the glass, attempting to separate it from the fuselage. The resisting force was the combined tensile and shear capacity of the bolts, multiplied across the total number installed. This distribution assumed uniform load sharing, an assumption critically dependent on identical bolt geometry and elastic behavior. When bolts of smaller diameter are substituted into such an assembly, the problem is not merely reduced strength. Smaller bolts elongate more under the same load due to lower cross-sectional area. This increased elastic deformation causes load redistribution. Bolts with greater elongation shed load earlier, transferring stress to neighboring fasteners. Instead of a uniform stress field, the system develops localized overloads. The structure does not fail symmetrically. It fails at the point where the imbalance becomes unsustainable. During climb, the aircraft experienced mild vibration from engines and airflow, while within expected limits. These vibrations introduced micro-slippage at the interfaces between the bolt heads, the windscreen frame, and the fuselage skin. In a correctly assembled system, clamping force would be sufficient to prevent relative motion. In this case, reduced bolt diameter and altered thread engagement compromised preload stability. The system entered a regime of progressive preload loss, invisible and inaudible, but mechanically decisive. At cruising climb speed, aerodynamic loading added another vector of stress. Airflow over the nose of the aircraft created pressure gradients that interacted with the curvature of the windscreen. Although minor compared to pressurization forces, these aerodynamic loads contributed to cyclic shear stresses at the bolt interfaces. Each cycle was individually insignificant, yet cumulatively effective at exploiting the reduced friction and clamp force present in the assembly. The cockpit environment provided no sensory cues. There was no cracking sound, no visible distortion. Laminated glass can tolerate significant deformation before fracture, and in this case the glass itself remained structurally intact until the moment of separation. The failure mode was not material rupture of the transparency, but fastener shear and pull-through at the frame interface. The windscreen was becoming mechanically disconnected while remaining visually unchanged. At approximately 17,300 feet, the pressure differential approached its operational maximum for the climb phase. The cabin pressure controllers stabilized the internal environment, maintaining comfort for passengers and crew. Structurally, this marked the point where cumulative bolt load approached the diminished capacity of the weakest fasteners. One bolt, likely experiencing the highest localized stress due to load redistribution, entered plastic deformation. Its elongation increased disproportionately, accelerating load transfer to adjacent bolts. This process unfolded rapidly, but not instantaneously. Structural failure in such assemblies often propagates through a cascade. One fastener yields, increasing stress on its neighbors, which then fail in quick succession. The timescale is measured in milliseconds, yet the underlying mechanism is governed by deterministic mechanics rather than randomness. The system crossed a threshold where equilibrium could no longer be maintained. When the first bolt failed completely, the clamping ring lost symmetry. The windscreen experienced a sudden change in boundary conditions, with one sector no longer restrained. Pressurized air exploited this weakness immediately. The internal pressure acted on the exposed edge of the windscreen, generating a peeling force that far exceeded what the remaining bolts were designed to resist in that configuration. Structural integrity collapsed not because of excessive overall load, but because the load path had been catastrophically altered. The remaining bolts failed in rapid succession, either shearing or being pulled through their mounting holes. The windscreen separated from the fuselage almost as a single rigid body. There was no gradual crack propagation, no warning deformation. The event was discrete and violent, defined by a sudden conversion of stored pressure energy into kinetic energy. The immediate consequence was explosive decompression localized at the cockpit. Air rushed outward through the opening, driven by the pressure differential, accelerating to supersonic velocities at the edges of the breach. The force vector was not evenly distributed. It followed the path of least resistance, directly through the vacated windscreen aperture. The cockpit became a conduit rather than a compartment. The captain, seated closest to the windscreen, was exposed instantaneously to this flow. The human body, unsecured against forward movement, became part of the pressure equalization process. Aerodynamic suction, combined with inertial forces from the aircraft's forward velocity, overcame the restraint of the seat and harness. This was not a failure of restraint design, but a consequence of force magnitudes far beyond those anticipated in cockpit survivability models. From a systems perspective, the event illustrated a fundamental truth about stress environments. They are indifferent to human presence. The same pressure forces that expelled the windscreen acted on everything in their path. The cockpit transformed from a protected control space into an extension of the external airflow in less than a second. Inside the aircraft, the rapid decompression triggered physiological stress responses. Cabin air density dropped sharply, oxygen partial pressure decreased, and temperature fell. Yet these effects were secondary to the mechanical violence of the event. The flight deck was now structurally compromised, aerodynamically unstable, and partially open to the atmosphere at altitude. The aircraft itself remained largely controllable in the immediate aftermath. The One-Eleven's flight control systems were mechanical and robust, not directly dependent on cockpit pressurization. Engines continued to produce thrust. Wings continued to generate lift. This dichotomy, catastrophic local failure within an otherwise flyable airframe, underscored the compartmentalized nature of aircraft design. It also highlighted how localized structural failures can produce consequences grossly disproportionate to their physical scale. The anatomy of stress in this event was not defined by extreme conditions. There was no turbulence, no overstress maneuver, no environmental anomaly. The aircraft was operating squarely within its certified envelope. The decisive factors were cumulative fatigue cycles, altered fastener geometry, and load redistribution mechanisms that transformed ordinary operational forces into catastrophic failure drivers. What failed was not the concept of pressurization or the strength of laminated glass. What failed was the assumption that a system, once assembled, remains what its documentation says it is. Stress does not negotiate with assumptions. It interrogates reality at the molecular and geometric level, exploiting every deviation until equilibrium collapses. In this case, the collapse was instantaneous, irreversible, and indifferent to the reputational confidence built around the machine. The aircraft continued forward, now carrying the full consequences of a failure rooted not in dramatic overload, but in mundane deviation. The invisible forces that had been acting since takeoff had completed their work, converting an error measured in millimeters into a life-threatening structural event measured in fractions of a second. The moment of failure was not an explosion in the conventional sense, but a rapid structural disassembly driven by pressure equilibrium seeking a new boundary condition. At the instant the final fastener lost its capacity to resist tensile and shear forces, the windscreen ceased to be a restrained component and became a free body subjected to a pressure differential of several pounds per square inch across a surface area large enough to translate that differential into thousands of pounds of force. The energy involved had been stored incrementally during climb, locked within the compressed cabin air and the elastic deformation of surrounding structures. Release was instantaneous. Frame-by-frame reconstruction shows that the initial motion of the windscreen was outward and slightly upward, following the resultant vector of internal pressure and external aerodynamic flow over the nose. There was no shattering of glass. The laminated structure remained intact, behaving as a rigid panel rather than a fragmenting element. This detail is critical because it confirms that material failure of the transparency was not the initiating event. The failure was mechanical and geometric, not brittle. As the windscreen departed the fuselage, it created an aperture directly ahead of the left pilot's seat. Airflow accelerated through this opening, driven by the pressure gradient between the pressurized cockpit and the lower ambient pressure at altitude. The flow regime transitioned immediately into a choked condition, where local airflow velocity reached the speed of sound at the boundary of the opening. Downstream of that boundary, airflow expanded and accelerated further, producing extreme localized suction forces. The captain's body intersected this flow path. The seat restraint system, designed to manage inertial loads associated with turbulence or deceleration, was not engineered to counter sustained aerodynamic extraction forces acting normal to the seating plane. The harness distributed load across the torso, but the vector of force acted forward and upward, effectively converting the restraint into a hinge rather than a barrier. The captain was partially ejected through the opening, pinned against the external fuselage by aerodynamic pressure. Physiologically, the exposure was immediately hostile. At approximately 17,000 feet, ambient pressure dropped to roughly half of sea level. Rapid decompression reduced oxygen partial pressure in the lungs before exhalation could occur, risking pulmonary overexpansion injury. Simultaneously, the temperature of the airflow dropped sharply, imposing acute cold stress. These factors compounded the mechanical trauma induced by aerodynamic loading. Inside the cockpit, loose objects were drawn toward the opening. Checklists, headsets, and unsecured items followed the same pressure-driven trajectory, impacting the edges of the aperture or exiting the aircraft entirely. Noise levels rose instantaneously to damaging levels, dominated by turbulent airflow and structural vibration. Communication between crew members became nearly impossible without deliberate effort and proximity. The first officer, seated to the right, experienced a sudden loss of visual reference forward. The normal horizon line was replaced by chaotic airflow and the partial obstruction of the captain's body against the fuselage exterior. Despite this, the aircraft's primary flight controls remained functional. Control cables and linkages were intact, and there was no immediate asymmetric thrust or control surface damage attributable to the decompression event. The aircraft's pitch attitude changed slightly as the sudden loss of forward fuselage pressure altered aerodynamic balance. The nose experienced a minor upward pitching moment due to altered pressure distribution, but this was within the corrective authority of the control system. Engine operation remained stable. The failure was spatially localized, not systemic. Time compression played a decisive role. The sequence from initial fastener failure to full windscreen separation occurred in a fraction of a second. Human perception lagged behind mechanical reality. By the time the crew could cognitively register that a failure had occurred, the event was already complete. This temporal mismatch is characteristic of structural failures driven by stored energy release rather than progressive degradation visible to the operator. From an engineering standpoint, the failure mode exemplified unstable equilibrium. Prior to separation, the system existed in a metastable state, capable of sustaining load as long as all components remained within elastic limits. Once a single element exceeded its capacity, the redistribution of stress accelerated failure rather than arresting it. There was no redundancy capable of arresting propagation once the first bolt failed catastrophically. The decompression itself did not propagate further structural damage along the fuselage. This is significant. The One-Eleven's fuselage skin and frames absorbed the transient pressure wave without tearing or buckling. The event remained confined to the cockpit opening, demonstrating that the surrounding structure retained sufficient margin despite the localized breach. This containment prevented escalation into a full fuselage rupture. The airflow through the opening exerted continuous force on the captain's body, effectively anchoring him against the aircraft exterior. Paradoxically, this same force prevented complete separation from the aircraft. Aerodynamic pressure acted as both the cause of ejection and the mechanism of retention, holding the body against the fuselage skin with sustained force proportional to airspeed and pressure differential. The crew's immediate response was constrained by physical reality rather than procedure. There was no checklist for windscreen loss with partial crew ejection. Actions were driven by instinct, situational awareness, and the mechanical priorities of maintaining controlled flight. The first officer reduced thrust and initiated a descent to lower altitude, aiming to reduce pressure differential and aerodynamic loading as rapidly as possible without inducing further structural stress. As altitude decreased, external air pressure increased, reducing the force driving airflow through the cockpit opening. The aerodynamic suction acting on the captain diminished accordingly. This relationship between altitude, pressure differential, and aerodynamic force was linear and predictable, even if its human implications were extreme. The descent was not merely a procedural response, it was a direct mechanical mitigation strategy. Throughout this phase, the windscreen itself was no longer part of the system. It had departed the aircraft entirely, likely shattering upon impact with the airframe or disintegrating in the airflow. Its absence altered the aerodynamic profile of the nose, introducing drag and turbulence, but not enough to compromise lift or directional stability. The aircraft remained flyable, a testament to structural compartmentalization. The moment of failure thus revealed a critical asymmetry between human vulnerability and machine resilience. The aircraft tolerated the loss of a major component and continued functioning. The human body, integrated into the cockpit environment, became an unintended structural element subjected to forces never anticipated in design. From a forensic perspective, the sequence was mechanically pure. There were no secondary triggers, no cascading system failures beyond the initial structural breach. The initiating event was the loss of fastener integrity. The subsequent events followed directly from fluid dynamics and pressure physics. Each step was governed by deterministic laws, not chance. The failure did not announce itself with warning signs because the system lacked sensors capable of detecting the precursors that mattered. There was no monitoring of bolt preload, No detection of micromovement or loss of clamping force. The first observable symptom was total failure. This characteristic differentiates catastrophic structural failures from gradual degradations detectable through performance anomalies. The moment also exposed the limitations of certification logic. Certification tests validated ultimate strength under idealized conditions. They did not model the consequences of incorrect component substitution that preserved apparent fit while degrading mechanical performance. The test environment assumed fidelity to specification, an assumption violated long before the aircraft reached the runway. In that instant, the boundary between inside and outside ceased to exist where it mattered most. The cockpit, designed as a controlled environment, became an interface with the atmosphere at altitude. Control remained possible, survival remained uncertain, and the aircraft carried forward the physical evidence of a failure that had already completed its primary destructive act. What followed would not alter the physics that had just played out. The decisive work of failure was already done. The remaining challenge lay not in preventing the event, but in understanding it, dissecting how a system built on confidence, redundancy, and certification could be undone by a deviation so small that it evaded perception until the moment it erased the boundary entirely. The forensic phase began not in a laboratory, but in the stabilized aftermath of an aircraft that had survived a localized structural breach without losing global controllability. Once on the ground, the event transitioned from an operational emergency to a material investigation governed by traceability, dimensional accuracy, and failure reconstruction. Authority was assumed by the United Kingdom's Air Accidents Investigation Branch, whose mandate emphasized causal mechanisms over culpability. The objective was not to assign blame, but to reconstitute the physical narrative embedded in fractured interfaces and substituted components. The absence of the windscreen itself complicated initial analysis. The primary failed component had separated from the airframe and was not available for immediate examination. What remained was the fuselage aperture, the windscreen frame, and the surviving fasteners, artifacts that collectively recorded the failure through deformation patterns, thread damage, and witness marks. Investigators treated the opening as a crime scene defined by load paths rather than by visual drama. Initial inspection focused on the bolt holes around the windscreen frame. These holes exhibited elongation and localized tearing inconsistent with uniform loading. The deformation was directional, indicating peeling forces rather than pure tensile separation. Such patterns suggested that the windscreen had not failed symmetrically, reinforcing the hypothesis of sequential fastener failure rather than simultaneous overload. This observation aligned with the mechanics of load redistribution predicted for assemblies with heterogeneous fastener stiffness. Recovered bolts were cataloged and measured with precision instruments. Diameter measurements revealed systematic deviation from the specified dimensions listed in the maintenance documentation. The discrepancy was small, fractions of a millimeter, but consistent across multiple fasteners. Metallurgical analysis confirmed that the bolts were of a different specification class than required, possessing reduced cross-sectional area and altered thread engagement characteristics. Crucially, the material itself met strength specifications for its own class. The failure arose from misapplication, not from defective manufacture. Thread imprint analysis on the fuselage structure provided further evidence. The depth and pattern of thread engagement showed incomplete load transfer between bolt and frame, consistent with undersized fasteners torqued to nominal values. Torque wrench readings during installation would have indicated compliance, masking the underlying reduction in preload capability. This finding underscored a critical vulnerability. Torque is an indirect proxy for clamping force, highly sensitive to friction coefficients and geometry. When geometry is wrong, torque compliance becomes meaningless. Investigators reconstructed the maintenance history of the aircraft, focusing on the most recent windscreen replacement. Documentation showed that the task had been performed during routine maintenance, not as a corrective action prompted by damage. The replacement followed standard procedures, and no anomalies were recorded at the time. The bolts used were drawn from available inventory, visually similar to the specified fasteners and compatible in length, allowing installation without apparent difficulty. The inventory control process became a focal point. Parts bins contained fasteners of multiple specifications, differentiated primarily by part numbers rather than by obvious physical features. The procedural assumption was that technicians would select parts strictly by documentation reference. In practice, visual similarity and dimensional compatibility allowed substitution without immediate resistance. The system relied on human vigilance rather than physical incompatibility to prevent error. Laboratory testing extended beyond dimensional analysis. Surviving bolts were subjected to tensile and shear tests to quantify their actual load capacity relative to the design requirement. Results confirmed that while individual bolts met their own specification limits, their capacity was insufficient for the combined loading environment of a pressurized cockpit windscreen. Finite element models constructed using measured bolt properties demonstrated that the assembly's safety margin had been reduced to near unity under normal operating conditions. Fatigue analysis revealed another compounding factor. Reduced bolt diameter increased stress concentration at the thread root, accelerating fatigue crack initiation under cyclic pressurization. Although no macroscopic fatigue cracks were observed in the recovered bolts, microscopic examination identified early-stage crack initiation consistent with elevated stress amplitude. This suggested that the assembly had been operating in a degraded state for multiple flight cycles, progressively eroding its remaining margin. The absence of corrosion or material embrittlement eliminated environmental degradation as a contributing factor. The failure was purely geometric and procedural. This distinction was critical, as it removed the event from the category of age-related degradation and placed it squarely within the domain of human-system interaction. The aircraft had not aged into failure, it had been assembled into it. Investigators reconstructed the failure sequence using computational fluid dynamics coupled with structural models. These simulations validated the observed deformation patterns and confirmed that once the first bolt failed, the remaining fasteners would experience rapid overload. The time to total separation was calculated in milliseconds, consistent with crew testimony and flight data. The model also reproduced the aerodynamic suction forces sufficient to partially eject a seated pilot, corroborating the physical plausibility of the observed outcome. Attention then turned to organizational factors. Maintenance procedures specified the correct fastener type, but did not require independent verification beyond task sign-off. There was no secondary dimensional check, no requirement to measure bolt diameter prior to installation. The system assumed that correct part selection was a solved problem. This assumption was embedded not in negligence, but in efficiency-driven workflow design. Training documentation emphasized torque values and installation sequence, but devoted little attention to the functional consequences of fastener substitution. The educational focus was procedural compliance rather than mechanical understanding. As a result, technicians could complete tasks correctly in form while inadvertently violating the underlying mechanical assumptions on which safety depended. The investigation avoided retrospective moralization. Instead, it framed the error as systemic. The maintenance environment allowed visually similar components to coexist without physical differentiation or enforced segregation. Documentation relied on alphanumeric identifiers rather than fail-safe design. In such an environment, error probability was non-zero by construction. The absence of prior incidents involving similar failure modes contributed to delayed recognition of the risk. Statistical safety bred confidence that the system was robust, reinforcing reliance on procedural compliance. The investigation noted that rare failure modes often persist precisely because they do not announce themselves through minor incidents. They remain latent until alignment of conditions triggers full manifestation. Physiological analysis of the captain's injuries, conducted alongside mechanical investigation, confirmed that survival was consistent with the aerodynamic retention hypothesis. The same forces that caused partial ejection maintained body position against the fuselage, preventing complete separation. This outcome, while extraordinary, was mechanically coherent and reproducible in simulation. It was not an anomaly, but a predictable result of airflow dynamics, given the specific geometry and flight parameters. The cockpit voice recorder provided limited additional insight due to noise saturation immediately following decompression. However, the sequence of events inferred from structural evidence aligned with recorded data, reinforcing confidence in the reconstructed timeline. The flight data recorder showed stable control inputs and descent initiation consistent with rapid situational assessment under extreme conditions. The forensic process thus converged on a singular causal chain: incorrect fastener specification leading to reduced clamping force, progressive preload loss, localized overload, sequential fastener failure, windscreen separation, and explosive decompression. Each link was individually comprehensible and mechanically sound. There were no speculative leaps, no unknown forces. The event was the deterministic outcome of a known system operating under violated assumptions. The investigation's conclusions were deliberately narrow. It did not indict the aircraft design as inherently flawed, nor did it characterize the event as unforeseeable. Instead, it identified a mismatch between design assumptions and maintenance realities. The aircraft was safe when assembled as specified. It was vulnerable when those specifications were approximated rather than enforced. In this sense, the forensic aftermath served not as a post-mortem of a machine, but as an audit of trust. Trust in documentation, trust in inventory control, trust in procedural sufficiency. The windscreen failure exposed how these forms of trust, while operationally necessary, can become structural liabilities when unaccompanied by verification mechanisms grounded in physical differentiation. The evidence did not suggest malice or recklessness. It suggested normal work conducted in a system that treated correctness as implicit rather than actively defended. The investigation concluded with recommendations aimed not at punishment, but at redesign of processes, of parts management, and of the assumptions that allowed a critical boundary to be secured by components whose adequacy depended entirely on human selection. The aircraft had returned intact. The evidence had been collected. The failure, now fully articulated in measurements and models, awaited translation into systemic change. The systemic legacy of the windscreen failure did not manifest as a dramatic redesign of aircraft structures, but as a quiet recalibration of how aviation defined correctness. The event forced regulators, manufacturers, and operators to confront a subtle but foundational vulnerability: the gap between engineered intent and maintained reality. The aircraft had not exceeded its design envelope. The materials had not degraded beyond expectation. The failure emerged from the assumption that specification compliance, once written, naturally persisted through human execution. One of the earliest outcomes was a reevaluation of fastener criticality. In many legacy aircraft designs, fasteners have been treated as interchangeable commodities within broad categories defined by diameter, length, and material. The investigation demonstrated that for pressurized boundary components, this abstraction was insufficient. Small geometric differences translated into large differences in preload behavior, fatigue life, and load-sharing characteristics. As a result, operators began to classify certain fasteners as safety-critical components rather than generic hardware. This reclassification had immediate procedural consequences. Parts management systems were modified to segregate visually similar fasteners physically, not merely administratively. Color coding, dedicated storage, and restricted access were introduced to prevent inadvertent substitution. The objective was not to improve human vigilance, but to reduce reliance on it. Error prevention shifted from cognitive discipline to physical constraint. Maintenance documentation also evolved. Manuals increasingly emphasized why a specification mattered, not only what the specification was. Torque values were contextualized with explanations of clamping force, elastic deformation, and load distribution. This represented a philosophical shift. Maintenance was no longer framed purely as procedural compliance, but as the preservation of structural assumptions made during design. Technicians were encouraged to understand the mechanical consequences of deviation, however small. Training programs incorporated case-based learning derived directly from the event. The windscreen failure became an instructional example of latent error propagation, illustrating how routine tasks performed correctly in appearance could undermine system integrity. Importantly, the narrative avoided personalization. The lesson was systemic, not moral. This framing reduced defensiveness and increased adoption, allowing the industry to internalize the implications without attributing failure to individual incompetence. From a certification perspective, the event prompted renewed scrutiny of installation tolerance assumptions. Regulators began to question whether certification tests that assumed perfect assembly adequately represented operational reality. While certification standards did not mandate testing with incorrect components, the incident reinforced the importance of design features that make incorrect assembly physically difficult or impossible. Where such features were absent, additional procedural safeguards were recommended. Design philosophy subtly shifted toward what could be described as error-tolerant engineering. Rather than assuming flawless maintenance execution, designers increasingly considered how systems behaved under plausible deviations. This did not mean accepting incorrect assembly, but acknowledging that human systems are probabilistic. Components critical to pressure integrity were redesigned with clearer differentiation, asymmetric interfaces, or unique fastener geometries to prevent misapplication. The event also influenced how safety culture interpreted rarity. Prior to the incident, the absence of similar failures had been taken as evidence of robustness. Afterward, it was reframed as evidence of untested vulnerability. Rare events were no longer dismissed as anomalies. They were examined as indicators of alignment between latent conditions. This reframing supported the growth of proactive safety analysis methods focused on identifying dormant failure modes before manifestation. Operationally, the incident reinforced the value of crew adaptability under conditions not covered by checklists. While the investigation focused on mechanical causation, the industry recognized that survival hinged on rapid, physics-informed decision-making rather than rote procedure. This recognition fed into training that emphasized principles-based understanding of pressurization, aerodynamics, and structural response, enabling crews to improvise effectively when formal guidance was absent. Philosophically, the windscreen failure challenged the notion that safety margins are static quantities. Margins exist only insofar as assumptions remain valid. When an assumption is silently violated, through substitution, approximation, or normalization of deviation, the margin collapses without warning. This insight resonated beyond aviation, influencing safety thinking in other high-reliability domains such as nuclear power and medical device manufacturing. The event also exposed the asymmetry between technological sophistication and vulnerability. Advanced aircraft systems had eliminated many complex failure modes, yet a basic mechanical interface became the point of failure. This inversion highlighted a recurring pattern in mature technologies. As complex risks are mitigated, residual risk concentrates in mundane interfaces where attention has waned. Safety, therefore, became less about mastering complexity and more about rigorously managing simplicity. In retrospect, the cost of progress was not measured in lost technology, but in shattered confidence. The cockpit windscreen, a symbol of transparency and control, became a reminder that no boundary is secure unless continuously defended. The industry absorbed this lesson not through dramatic reform, but through incremental tightening of the relationship between design intent and operational execution. Today, the legacy persists in checklists that ask different questions, in parts bins that enforce correctness through design, and in training that treats understanding as a safety device. The windscreen failure is no longer viewed as an aberration, but as a case study in systemic fragility. It illustrates that safety does not erode through dramatic neglect, but through the quiet acceptance of approximation. The aircraft involved returned to service after repair, structurally sound and mechanically restored. The system, however, did not return unchanged. It carried forward a revised understanding of how easily confidence can outpace reality. In that recalibration lies the enduring legacy of the event, a recognition that the true cost of progress is vigilance, paid continuously, in increments too small to notice until they are absent. In aviation, boundaries are defined not only by metal and glass, but by discipline, verification, and respect for scale. The windscreen failure demonstrated that a deviation invisible to the eye can nullify decades of accumulated safety knowledge. The response was not to abandon confidence, but to ground it more firmly in physical truth. The lesson endures because it is uncomfortable. It offers no villain, no dramatic overload, no exotic failure mechanism. It reveals that even in the most regulated environments, the margin between safety and catastrophe can be consumed by ordinary work performed under ordinary assumptions. That realization reshaped how aviation thinks about its most trusted systems, not as static achievements, but as conditions that must be actively maintained. The final legacy is not embedded in a redesigned component, but in a cultural shift toward humility before mechanics. Progress continues, but with a clearer understanding that complexity does not eliminate basic risk, it merely relocates it. The cost of that understanding was high, but its value persists every time a component is verified not because it looks right, but because it is right.